Hey folks. Well, I want to switch gears a little bit, and now that we've talked about sort of the lex and yak and context-free grammars and scanning and parsing a language, I want to talk a little bit about the named items in a language, or in specifically in an active program, if you like, and what kinds of information we want to be able to associate and use with that name. So there's a whole slew of different things that we might consider as named items in a program. Right? You've got variables, constants, functions, parameters, labels, the structures, data types, the fields of structures. So there's all sorts of different types of things that are going to get named, and somehow we have to know what information to keep track of for each of them. And so there's a whole slew of different attributes that we might want to keep track of, right? For a variable, you've got its data type, you've got what value is currently stored in it, you've got its memory address, you might have what kind of memory storage it's using, or what kind of data storage it's using. So there's all sorts of different kinds of information to keep track of, and what I want to talk about in our session today is just to highlight some of those things, and also to look at when those values get set or associated with a name, and at what point they might change, and at what point they might be dropped. So we want to look at what kinds of attributes can be associated with something. We'll talk about binding an attribute to an item, basically saying, okay, this is when we actually associate this value with this attribute of this item. So when that takes place, whether or not it can change later, and just highlight some of the issues that go along with this, because it does have a lot of implications when we look at the implementation of our language, when we look at creating things like compilers for our language, and how they translate our high-level code into something like assembly language. So that's kind of where I want to go. So thinking about the different kinds of named components we might have in a language, we've got some alphabet that we've chosen for our language, right? Some alphabet of possible characters in the source code for our language. And we've looked at regular expressions to go through and describe what the individual tokens, the individual components of our language happens to be. So I'm going to kind of carve up names a little bit, and we'll talk about keywords, reserved words, predefined names, and user-defined names. And so the idea is the reserved words are the most restrictive ones. Those are the things that have a single fixed meaning in your language. So maybe in your language, the word while can only be used as the start of a while loop. Right? So reserved words are words that have one specific universal meaning in your language. Keywords are similar, but they might only have a meaning within a specific context. So maybe if you're in the context of performing a variable declaration right now, int is a keyword for a type, but everywhere else you can use it as a variable name. It seems like kind of a crazy idea, but it's a possibility. So the idea of having words that are only reserved, if you like, in a specific context. Otherwise, you can use them more or less like regular identifiers. So predefined words are words that have been already defined at some point in our program. So maybe it's because we hash included a library or something like that, and they were declared in the library. But so they have a meaning associated with them, but maybe we can override that meaning or override that name. And then user-defined words are the ones that we go through and declare in the source code itself. So we create a variable or whatever it might be, or we create a function or a parameter. We make up the name for it. So we've got this different sort of hierarchy of things and how much power the programmer has to reuse that name in a different way at different points in the program. Now, it's not something we think about a whole lot, but the language naming rules does have a big impact on how you actually wind up using the language and sort of the culture of use that you develop for a language. Are names case sensitive or not? If you've got some variable with the S and the V uppercase and everything else lowercase, and then you've got another variable, some variable where the S is uppercase but the V isn't, do those represent the same variable or not? Is there a maximum length for your names? Is there a minimum length for your names? One of the interesting quirks many moons ago was that in BASIC back in the beginning, you could have long variable names, but it only looked at the first three characters when it actually thought about it as an identifier. So if you had myvar1 and myvar2, those would actually be the same variable, even though to you as a programmer, it looks pretty much like they should probably be different variables. So again, you see some interesting quirks when you're looking at different languages, and they all have different implications, right? If you're thinking of case sensitivity, it's nice as a programmer to be able to create slightly different names that use case to identify something. You use case to identify whether it's a constant or a variable, or maybe you use case to indicate whether it's a global or a local. Or sometimes it's nice to have that flexibility. On the other hand, if it's case insensitive, then you don't have to worry about your sloppy typing. You can fat finger something and wind up with the same variable name. So there are advantages and disadvantages either way. Of course, the alphabet that you're using is going to be significant for the developer, right? You'd like the flexibility to have a wider range of characters available to you. Maybe I'd like to be able to use Unicode in my variable names. You want to think about whether or not there's overlap between the user-defined names and other names. If you're, and again, we've looked at some of this with the sort of Lex side of things. If you can take a variable name and give it just digits, so maybe 1, 2, 3 is a valid variable name, during the course of parsing, your program has to be able to figure out whether you're using 1, 2, 3 as the integer value or using it as the variable name. So you do have to think about the impact of the naming rules for your language. All right, I want to look at a whole slew of different kinds of attributes that we might play with. So I'm going to think of this primarily in the context of variables for now. Later on, we'll come back and talk about similar ideas with functions and other things, and data types and whatnot. But for now, if we're thinking about a variable, what kinds of things do we want to associate with a specific variable during the run of the program? Right? We've got the name for it that we see in the source code itself. We've got the location. So where is this thing actually going to get stored? Is it in a memory address someplace? Is it stored actually in a register someplace? Where is this variable going to get stored? What value is currently associated with it? What data type is currently associated with it? What's its lifetime? When does that variable come into existence, and when does it cease to exist? So does it exist for the entire run of the program, or just for the run of a single function call? Right? When does this thing exist? And then scope. Where is it accessible? So in our source code itself, where can I get at that particular variable? So all sorts of different attributes. And again, we want to think of this in terms of both the kinds of values that are specifically here, and we also want to think about when a value gets bound to these different attributes. When does the name get assigned? When does the location get assigned? When does the value get assigned? And can these things change over time? Can I move a variable from one location in memory to another location in memory? If so, what are the implications for that? So we'll talk about static and dynamic binding. Static binding for an attribute means that we choose the value of that attribute at compile time. So as soon as the program is compiled, we know the value of that attribute for that variable. So going back and looking at these sorts of things, typically our names are going to be statically bound. Typically, if you're looking at a language like C++ or C or something like that, the data type for it is statically bound. We know at compile time what its data type is going to be. We know at compile time what its scope is going to be, right? We can look at the source code and say, okay, well, it's accessible here, here, and here, right? We can look at it and identify what its lifetime is going to be. Its lifetime is going to be, it's a global variable. It's going to exist for the entire run of the program, or it's local to a function. It's going to exist from the beginning of that function to the end of that function, from the beginning of that function call to the end of that function call, right? So we can look at a number of attributes for variables or for functions or other things, and figure out whether they're statically bound or not, figure out whether those things are set at compile time. Now, if it's not set at compile time, if it isn't set until the program actually executes, then we say it's dynamically bound. That attribute's value is set at runtime, dynamically bound. And if it is dynamically bound, then we also kind of want to know if it can change later. Right? Obviously, the value that's associated with a variable is something that is going to get set during execution and can change. Right? So it's dynamically bound, and it can change once it's bound. So we'll take a look at static and dynamic binding for each of these attributes. And for dynamic binding, we'll take a look at whether it's sort of set once at some point during execution, or whether it can change over the course of execution. All right, so again, just thinking about some of the examples we had there. If we're looking at a name, it's static in C. In Lisp, we can go through and as a program executes, we can create new symbols, so we can create new names. The address, the storage location, where is this thing going to live in memory or in registers or wherever it is it's going to exist on the stack. So, typically we're going to think of this kind of thing, especially for variables, as something that happens dynamically. Now, it's possible that, in some language, in some languages on some systems, you can go through and say, okay, I want this variable to exist at memory address blah, in which case you're setting it statically, right? You're in the source code someplace saying this is where it must live. But generally speaking, when we're talking about variables in modern high-level languages, we're talking about a dynamic binding of where the location is. And of course, we're interested in whether that can change or not. Can a variable move from one memory location to another during execution? And of course, if you're playing with something like C and you're allowed to take pointers to things, that would have some really serious implications later on. And if somebody moved the variable and you had a pointer to it, and effectively you wind up with a dangling pointer. Values. Typically, our values for variables are dynamic. It's set during execution, and it can change. The data type. Again, static in C, but if you've got a language like Lisp, your data types are dynamic. Right? The data type is actually associated with whatever value is currently stored in a variable, not with the variable itself. If you're looking at variable scope, again, our typical C-style approach is just lexical scope, but we've seen in Lisp the possibility of using dynamic scope as well. Right? So these are things that can be static or dynamic. The lifetime of a variable, when it comes into existence and when it ceases to exist. Is this something that can be determined by the scoping rules? Is this something that we can exactly identify from the source code itself? And then we get data typing. I want to talk about typing in particular because it does have such an impact on our kind of life as a programmer. If you're using static typing, then you're saying that I assign the data type for everything at compile time, right? For every variable, for every parameter, for every array, for every whatever it is I create, I say here is its data type, and the compiler can actually go through as it's compiling and check and make sure that all of the types are compatible with the operations where they're used. Right? So the data type is determined by the source code. It's either explicitly declared or there's some kind of implicit declaration. So in something like Bash, where everything's a string by default. Or in some cases, there's a particular character that you can use or sequence of characters you can use in the name that dictates what its data type is. So for Perl, for instance, special characters in the name dictate what kind of data type it has. Now, if we're looking at dynamically typed languages, then if we think of the sort of Lisp style, sort of true dynamic typing where the data type is actually associated with the value that's currently in a variable and not with the variable at all, that's probably the most flexible format and the one that we're used to thinking about. There are also languages where you use dynamic typing, but it's fixed. So you don't determine the data type of something until execution, but as soon as you put a value of some specific type in a variable, that data type for the variable is fixed. So if you stick an integer in it, then from that point on, that variable is just for integers. Or if you stick a string in it, then from that point on, that variable is just for strings. So there are all sorts of possibilities, again, with static and dynamic binding. Obviously, we've seen in playing with Lisp some of the advantages and disadvantages of dynamic typing. It means that you can be way more flexible in passing stuff around. You can pass anything to a function. If if I've got a function that's supposed to work with a date, I can pass it, I don't know, the Julian date, or I can pass it a string, or I can pass it anything I want. It's way more flexible for the developer, and I can have a single function that takes in all sorts of data in different kinds of ways and does something with it. But of course, it means that when I actually go to write that function, I have to come up with all of the runtime type checks that are going to make sure, that are going to figure out what kind of data I got passed and is it appropriate, and then do something appropriate with it. So it can be really flexible, but it can also involve a lot of extra work at that side of things. Right? It prevents any compile time checking if you're using true dynamic typing, and that means that all of that work has to be done at runtime, and it typically means that the developer has to come up with their own rules for doing a lot of that. Right? Obviously, it can result in uncaught errors if we miss something, right? Where I accidentally put a string in something that I meant to be an integer. So you don't get type checking, so you don't get a warning, something blows up at the last minute. One of the interesting things that's tied to our dynamic typing is if a variable has a dynamic type, if it's got no fixed data type associated with it, then how do I figure out what the storage for that variable is supposed to be? If I'm going to put this variable in memory, or I'm going to put it on the stack or something like that, then what is it that I'm going to allocate as space for that? Maybe it's just going to hold a single character, and then later on it's going to hold a double, and then later on it's going to hold an array. What am I going to do in terms of allocating storage? I can't allocate the biggest possible storage. Well, I guess I can allocate the biggest storage size possible and just not use most of it most of the time for that variable. Or I can pick something common, or I can pick whatever value is first associated with it. Or you can take the kind of Lispy approach where you say, well, what I'll do is actually make the variable itself a pointer. So I'll set up a pointer in the stack for that. If the variable is a local variable in function, then I'll just have a little pointer in there, and that will point at whatever data value is currently associated with the variable. So the data values will be off in the heap someplace, and the variable will really just be a pointer that points to wherever that thing is. Or maybe if the data value is something that's small enough to fit in the same space as a pointer, I'll use it just directly, and otherwise I'll use a pointer. But again, there are options that we can take. All right, storage and lifetime. Where does the variable exist? When does it exist? When is it created? When is it destroyed? And so here I'm going to assume that we've got the typical approach. If we've got a runtime stack that we're using for the frames for the individual function calls, and then we've got a heap for dynamic allocation and deallocation. So the idea is our static variables are the ones that are going to be created, essentially specified by the compiler. These are the ones that are going to exist for the entire run of the program, pretty much. So typically, these are going to be created and assigned a location as soon as the program's loaded into memory. So these might have, there might be some fixed block of space off someplace to hold our static variables. So they're going to exist for the entire run of the program and then cease to exist when the program gets dumped out of memory. So this is the approach. If we're looking at something like C, then this is what's going to be used for your static local variables. They're all going to exist somewhere off in a predefined area. This is where your global variables are going to live. And so there are a variety of things that are going to be set aside in this kind of static space. Then there's the stack dynamic variables. So these are typically things that are local to a function call. So they're created and bound to a location when the function gets called, and space gets set aside on the stack, and they cease to exist when the function call ends, when it returns and that stack space is cleaned off. Or the heap dynamic ones, This is our typical Maliki, Kaliki kind of idea, or where you create an object in whatever your favorite OO language is, and somewhere off in memory, there's this big heap collection of memory space, and it gets created in there someplace, and there's a handle or a reference or a pointer that tells you where it is and gives you access to that space. So typically, here, the space isn't specifically tied to an individual function call, right? There's some other mechanism for deciding when it gets created and when it gets destroyed. And we will come back and spend a fair bit of time later looking at how we can maintain a sort of clean heap space. But we'll come back and look at that later. All right, now we've looked at lexical scope and dynamic scope, right? The sort of lexical scope, the typical C-ish approach or Java-ish or whatever it is you like, or the dynamic scope that we looked at in Lisp, where the what you can see, where you can see a variable can depend on the call sequence. So in a lexically scoped approach, you can look at the source code and know where something is accessible. And the typical approach is when you see a name used, you go through and check the innermost scope first. If it's not there, then you check the scope that surrounds that. And if it's not there, you check the scope around that. And you keep going until eventually you reach the global scope and either find it or fail. And then again, with dynamic scopes, you can create an item in your own scope and then say, okay, this is going to be available to anybody that I call, and anybody that they call, and anybody that they call. And so you've got this runtime behavior that defines where something is visible. And of course, we've seen some of the advantages and disadvantages of that. It can get a little weird to go through and try and debug things that are dynamically scoped. It can be really useful for settings where you want to be able to use, if you like, a current setting for something, and you want your functions to be able to change that, and you want it scoped, but you want it scoped based on the call sequence. So if I set the variable and call somebody, then I want them to use my setting. But I don't want to change some global variable that would have been in use by whoever called me. So you've got this sort of layered approach to things where I want the call sequence to have an influence, but I want some control over that influence. So I don't want it to be truly global, but I do want it to be visible to people that I call, to functions that I call. All right, and again, this can cause debugging issues, but it improves the flexibility as far as the developer is concerned if they're willing to put in the extra mental effort to comprehend what's going on. And if they're willing to put that burden on anybody who's going to maintain the code in the future. All right, so I think that's a kind of good general overview to the different binding aspects we're going to consider. We'll get into lots more specific details with individual features and individual attributes as we work our way through the next few weeks.